Hi, my name is Andrew Wicks. I'm a first-year PhD student at the DKF where my day job is working on early gastric cancer initiation. Today, I'm here to talk about regarding the CAMDA health privacy competition. My submission was titled Differentially Private Non-Negative Matrix Factorization. So I think from this conference, we're all aware of the massive amounts of data that are being generated across many different hospitals, institutes, universities, companies. And of course, there are a lot of efforts to organize this information into something usable for the research community of UK Biobank, NCBI, et cetera. This leads to the problem of synthetic data sharing. This is a data transfer agreement, which some people may have PTSD from. But there's a lot of regulatory bodies involved. And of course, this becomes a bit of a time-consuming and expensive task. So in terms of, but of course, it's vital for patient privacy to have these regulatory bodies in place. So synthetic data generation has been around for a long time, both in terms of bolstering the amount of data that we have available to us, but also from a privacy perspective. These are two highly simplified examples of paths one may take to do this. You may have some static function f of x, for example, where you're taking a data entry and turning it into something else. However, this is subject to something called a linkage attack, whereby an adversary may learn what f of x is and then have a direct one-to-one mapping back to the original data. Something slightly more, again, this is a hyper simplified example here, and there are, of course, non-parametric approaches as well, but one may also learn some underlying distribution of that data, or either a feature or a number of features from each data point, and then do a random sampling to generate synthetic data in that way. Of course, this is a much cheaper approach. The idea here is that it'll facilitate data sharing and thereby increase research potential. So we're going to focus more on this lower approach today. I mean, this is kind of how all the methods that I think myself and the others have followed. So this is a nice little flowchart that helped my understanding of a membership inference attack a lot. This is from this paper referenced down below. And the idea here is that some adversary may have a set of targets, and the idea is they want to query either a generator or a discriminator, in our case, generators, to try and learn if that synthetic record was involved in the generative process. This can be done in a white box or a black box approach. White box being that the adversary has access to the model's parameters and architecture. Black box being, and there are some movable definitions here as far as black box goes, but the idea is that they would not have this access. So there are lots of approaches for doing this. In recent years, people have come up with many different approaches, and generative adversarial networks, Monte Carlo reconstructions, training shadow models, as I think was mentioned previously. But the general idea here is that it's kind of becomes a problem, as you can imagine, for example, an HIV clinic or some clinic that notoriously has private information. A patient wouldn't necessarily, the clinic may want to release this information for the research community. However, patients wouldn't want that information to be disclosed. So the attack would then, by inferring member of this generator, you've now inferred that the patient was part of that set, and that set is the clinic, for example. So then you can actually use that feature that you've just learned to launch other attacks. And as we're just hearing in our panel discussion, where you can perform these imputations where you have available information across different sectors from the same or similar patients, where you can use this to attack. So it's bad. So as we learned before, there is a kind of a balance here. And ideally, we try to maximize both of these, utility and privacy, but we've got a little bit of a balancing act between these two, where as you try to improve one, you usually have sacrifices in the other. This, of course, is a little bit case dependent. And in the terms of health information, I think we'd like to err on the side of privacy. So the reason that I'm here today is for this CAMDA challenge. This is the graphical abstract that you're seeing on the left side of the screen that you've probably, if you were here for the last session, you've seen it before. I participated on the blue team side, whose goal was to generate the synthetic data set from the 3 provided data sets, which were 2 bulk RNA sequencing data sets and 1 single cell RNA sequencing data set. I am going to focus on the single cell approach here. I mean, the method that I'm going to present is the same for both. However, the brief data that I'll present is based on the single cell approaches, just for the future. 2 other important features: the baselines that were provided that were briefly mentioned before. One is this DOMIAS density-based membership inference attack on the red side, which is a package that's available. The other is a simple Poisson sampler for the single cell. So a little bit more background before I jump right into the method of non-negative matrix factorization. For those who aren't totally aware, it's essentially a matrix decomposition method whereby one seeks to minimize this Frobenius norm equation which is the square of the sum of squares between two matrices by using these update rules here. There's many ways to do this. This non-negative approach was from this 1999 paper here, whereby these update rules were derived from the partial derivatives as well as auxiliary functions to compute these. And these are just run iteratively until there's a convergence of the Frobenius norm or plateau. Rank K here, for example, is defined by the user. So that's going to be the size of the resultant matrices. If I mention bases or components or activations coefficients, these are described above as W being the basis components and H being the activations coefficients. NMF, and my inspiration for doing this is used a lot in biology, especially in the last decade or so, with one maybe familiar with somatic mutational signatures, which one method relies on, as well as now with single cell RNA sequencing has come to rely on some of these learning kind of cellular programs. It's effectively a feature reduction technique that has been used in this way. Differential privacy we'll cover briefly. This is the idea where you can inject noise into a sample to cover up the presence or absence of a specific sample in that set based on some query F. And that query F, it may be defined by the actual kind of data that you're looking at. And it's actually going to be done in different ways for different kinds of approaches. But the idea here is that you're injecting enough noise to hide that whether an adversary computes a statistic, they can find out whether a specific sample was in that set or not. So here's an overview of my method. I will walk through each step one at a time. Here is where differential privacy was optionally injected. I set this all up in a command line interface that is available. I'll share at the end if anyone's interested. But the idea here is just tunable by flags, and we can kind of test out combinations or just independent components of differential privacy here. So as I mentioned, the first step of this method is going to be non-negative matrix factorization, whereby you can imagine X is just going to be your simple RNA count matrix. I used a K as set to 50. This was just based on this simple elbow plot here, whereby on the y-axis you have the Frobenius reconstruction error, and on the X you have K. So you kind of see this start to plateau at around 50. So once we have performed this, this W matrix is taken into two very familiar algorithms. One is k-means, the other is going to be a random forest. The idea with k-means is k is then set to the number of cell types that is given in this case it was 14. That's given in the original data set. And the random forest essentially just serves as a mapping between the W matrix and the cell type labels. Keep in mind that on the M axis here, they're all indexed to match the original X matrix, which we'll come back to in the next step. So this was just trying to make a little bit of a visualization for understanding, whereby the colors that you're seeing overlaid on the matrices are going to be those K. These are just completely arbitrary, obviously, are just K assigned clusters, right? So once the cluster assignment is made from that W matrix, it's then mapped back onto X. From that, we can learn per cluster, per gene sample statistics. In this case, it's going to be the mean, standard deviation, and the zero odds frequency are computed on a per gene, per cluster level. From those, then we can use a sampler, Poisson or zero inflated negative binomial. It turns out Poisson worked a little better as far as utility went. Was used to then create X prime, where I'm just effectively taking random samples based on these learned statistics. Those summary statistics were an optional point of differential privacy for me, where I injected noise into those actual statistics to shift them a little bit. It's maybe worth mentioning, I think I actually skipped over how differential privacy was added to the k-means. This is just the previous slide, how it was added to the k-means. So that was just the centroids were perturbed with some place noise, and then the clusters, each value is reassigned based on the perturbed centroid. So as we mentioned in the last slide, we now have X prime. X prime is then taken either with the original H or with H prime, which is the third NMF maybe source of DP, differential privacy, where Gaussian noise is injected across H at a very low level because it actually gets pretty messy if you go any higher. And W prime is then derived from this. W prime is then that random forest that we trained earlier is then used to just assign the cell labels to X prime here. And this is where we're going to have our final synthetic data. So as far as the conditions that I did test, this is just an overview of what we're looking at. No DP is going to be no differential privacy at all. So that was just going to be the baseline non-negative matrix factorization method that I just walked through. NMF DP, this is going to be, again, Gaussian noise injected over H prime. K-means DP, the centroids are perturbed by Laplace noise. Sampling DP, the summary statistics are perturbed by Laplace noise. All of them self-explanatory. All of the flags were turned on at the same time to include all the differentially private steps. And the Poisson, as I mentioned before, the contest shipped us this Poisson control as our baseline. Control maybe a strong word here, but more of a baseline was really used for the Poisson, as I mentioned. So here's results from the baseline red team membership inference on a donor level for the single cell. And what you're seeing here is an area distributing operating curve showing basically a complete failure of the model, which is a good thing in the sense of privacy, where we have the diagonal represents a flip of the coin. And it basically showed a complete failure of the model. And, again, this is a good thing, but when it came to me trying to draw a conclusion about whether or not my method actually improved the privacy at all, it was completely useless for me, right? Because they all had pretty much equal resistance, basically to an ineffective attack, is what this essentially was. So I went and made a slightly more advanced attack where, again, and this is the same for the Domias. So when we're talking about like a partial black box here, so there's no awareness of the parameters or architecture of the generative model. What the model is given is, but the adversary is assumed to have some knowledge of some set of trained data that was in and was not in the generative process. So the idea is you're just trying to build a model that can predict membership based on knowledge of a very small subset of that training data. So basically, this simple. I know these model flowcharts are kind of a headache, but the idea here was just to make a slightly more sophisticated attack to see if it would make any difference in these ROC curves. So I basically just trained a simple autoencoder on the train data. This then was used to have that small subset of the train in and train out or hold out members, as well as synthetic data, to create basically just narrow down that 20,000 gene feature list, which is, I think, many of us are used to seeing, into a 20-dimensional vector. Then for the 21st feature, I just computed a nearest neighbor distance between the synthetic and the real, between the synthetic holdout and the synthetic in members. And this is a very common practice for these membership inference attacks. So once this was trained, I have my reduced representation space of those 21 features. I then just trained a simple binary classifier neural network. I'll show you the architecture in the next phase. It was nothing impressive, very simple neural network to get a slightly better result. And this was again, good defense here from even the Poisson. But you're seeing now the Poisson, which has the arrow pointing to it, starting to break down a little bit. So we're starting to get a little better performance against the Poisson with this slightly more sophisticated attack. Here you're seeing the none. So this was my baseline method where there was absolutely no differential privacy. So an improvement from the Poisson. And then every other line that you're seeing is the differential privacy steps. And there's no real difference between any one particular step. And this is, I'll get to my little discussion at the end. But the idea is that, any level of differential privacy had a nice preservation there. So then I wanted to go on for some statistical similarities or test utility. This was again provided by the contest. So I really didn't stray from the utility at all. I really just used their metrics. And what you're looking at here is SCC, Spearman correlation coefficient of the top 1,000 highly variable genes. And there's a nice slight improvement over the Poisson here. But as soon as differential privacy is added, you start to see that kind of drop off pretty significantly to get to all. The adjusted RAND index, the ARI, this is a comparison it's a pairwise comparison between the cluster assignments, between the real and synthetic, as well as the cell label assignments between the real and synthetic. So again, you're seeing kind of the same pattern here, where there's a little bit of an increase with the no differential privacy. However, when differential privacy is added, there starts to be a little bit of a drop off. This is just a qualitative look at the UMAP projections between the real and synthetic data that was generated. So for the final utility test, I ran Cell Typist. Again, this was provided by the contest. This is just a pre-trained model for a cell labeling task. I use the immune all high model if anyone is particularly interested in that. And here what you're looking at is just a comparison of the real the none, NMF, and all, I dropped the notice you'll drop by k-means and sampling as I didn't want to clutter up the slide, and they had almost identical performance to the NMF. So, and the title of the talk was DP-NMF, so I figured it was more important to focus on that. So again, what you're looking at here is a significant drop in the adjusted RAND index. This is going to be the same set, although a comparison between the real labels and the cell typist expected labels. So key to note here on the Jacquard index, which is just the intersection divided by the union here. So what you're noticing is a pretty significant drop off when in my method standalone, as well as any level of differential privacy. So here's where you're going to start to see that pain and utility. Again, this is just kind of a test of cell typist in and of itself in a way. But the idea remains that there is a pretty significant drop between the real and my values. So that's kind of just all I'm trying to say here. Any of the synthetic methods really do show a pretty significant drop off. So as far as some limitations, I think of what I've done here is, there's a high dependence on hyperparameters. I mean, this could be viewed as something that could be positive and leveraged, but it also is something that kind of limits all of the edge testing that you can do in a way, at least with my 2018 Mac Mini. So another limitation was independent treatment of the genes. So you remember my sampling approach, I computed I tried to make very clear the per gene, per cluster statistics that were computed, and they were sampled in that exact manner. So I kind of lost some of these higher order connections, which I think is what we're looking at when we see the adjusted RAND index scoring from the cell typist. There was a little bit of a privacy improvement, less so a utility one, and it could get computationally expensive at high scale to do this. So I think going forward, I would like to implement maybe a multivariate sampling strategy where it's just a little bit more complex to try and capture some of those higher order connections. A unified privacy budget for the command line interface. So the way it stands now is the user defines privacy budget, that epsilon value. That they define that for each individual step of differential privacy. I'd like to test an NMF backbone on some other, generative approaches, generative adversarial networks or variational autoencoders. As a full disclosure, I know it's not best practice in a talk to kind of discuss non-presented results, but I did run a test on perturbing the W and H matrix with variational autoencoder, and it really destroys the utility. So I mean, that's really what made me so careful about, and most of the noise that's injected really is in the sampling and the centroid perturbation stages. As soon as you kind of try to play with that matrix, and it makes sense, I mean, from a mathematical perspective, because it's very sensitive for the neighborhood effects of the reconstruction. So again, more sophisticated membership inference testing, I think, would be something that could be very useful in this case, because I would love to really push the boundary and see how much privacy actually can be preserved here, and a classic grid search for parameter tuning. So thank you very much. I really want to thank the organizers for inviting me here. This was a great opportunity, and if you're interested in the GitHub repo, there it is. Thank you.
Thank you so much, Andrew. Any questions from the audience? If there is none, I will just ask one question and in the interest of time. So I was just wondering, while you were injecting different differential privacy in different levels of your methodology, were you using like epsilon equally or?
No, so I was using it in different values. And that's kind of what I was mentioning, briefly before. It's very user defined. So there was a much tighter epsilon, smaller epsilon for the sampling, whereas there was a large epsilon for the H injection, just because, as I noticed, this was more sensitive. I think, I'd like to go, if I had a little more time, I could do exhaustive epsilon testing across all the different stages and have like that nice, AUROC chart where it shows, like, as I inject more noise, it kind of gets safe, more private. But
yeah, I think it would be great to see if you will do some type of ablation study.
Yeah. I think this is where the unified privacy budget comes in. I think would be nice to like kind of try and balance it and have it like built in where the model can actually try to it can try and balance it itself and optimize itself without like just brute force human approaches.
If there is no question, then we can maybe proceed with the next speaker. Thank you so much again.
Thank you.